Okay, so I'm going to go ahead and skip forward in the textbook, and so now we're going to skip ahead to chapter 5. Okay, and chapter 5 is on classification. So, you know, we left off chapter 3 with kind of just an basic introduction to some Bayesian principles and ideas, and I apologize, I'm writing up homework 3, so you guys get to kind of see this Bayesian stuff in action and just see how, you know, you start with a prior, and based on your data, how your posterior acts basically as a updated version of the prior distribution. It looks like my screen is freaking out here for a second. Let me pause. Okay, so we're skipping ahead to chapter 5, which is on classification. Okay, and so the idea behind classification is, you know, you see data. You have, let's say, data x, okay, x1 through okay, and we'll say, you know, each x, how many, what's our dimensions of this? What letter do they use here? We'll just say, okay, we'll just say each x, you know, is a vector in D space. Okay, and what we want to do is we want to classify this so that our t sub 1, t sub 2, t sub n, t sub each t is equal to, is it working or not working?
It's not working.
Oh my gosh, it flashes on and off. Okay, so basically, well, all right, okay, so t sub n is, you know, I don't know what to do. Okay, is an element, you know, from 1, 2 through c, representing a class. Okay. Okay. So, and this, I guess this is a classification. Okay. And basically, you know, all we need is just some way to go from here to here. Okay. So we've already seen this. Our artificial neural network, so was an example of a way to classify our data, right? Was an example of a classification method. And in that scenario, each vector x, you know, was, let's say, in our, let's do the digit recognition. Each vector was something in, I think, was it 28 by 28 or something? I forget. 28 by 28, however many 28 by 28 pixels, okay, was however many we had there. And then our each t was taken from basically the digits 0 through 9, right? Okay, or for the iris data set, x was in 4 dimensions. And t was an element of whatever, Virginica, Setosa, and I don't, what was the other one? Versicolor, all right? But we would probably just label these 1, 2, and 3, okay? And the hope is to, you know, we desire a model so that a new vector of x observations, which we will call x new, will give us a prediction of our class. Okay, and this will be, we will denote that t new. This is our prediction of class. All right, and so this is our, this is just the general classification problem, and we've seen an example of this. Have you guys taken 100C and you learned logistic regression? No? Yes? Okay, well. So, are you familiar with logistic regression? Okay, so logistic regression, that's an example of a classification problem. You're going from basically some numeric inputs, some x values, and it classifies it either as a 0 or a 1, right? And the output that it gives is probability that it's a 1, and because it's dichotomous in nature, you know, probability of 0 is 1 minus the probability of 1, okay? All right, so other examples, you know, logistic regression. Is an example of a classifier. It is a dichotomous classifier, okay? Okay, so your x inputs get mapped to either 0 or 1, okay? And this is kind of what we have here. Okay, so today's lesson, or today's lecture, will focus on what we call a Bayes classifier, okay? And specifically, we'll take a look at, okay, so let me just start off with the Bayes classifier, and then we will have slash the naive Bayes classifier. How do you spell naive? There's like a double dot over the I? What is that anyway? Classifier. Well, umlaut is for German things, and it's only over the O and the U. I don't know. Okay, well, whatever. Are there other words in English that have the double dot over an I? Okay, well anyway, okay, so let's, so basically what we want to do is, you know, this is what we call a probabilistic classifier. Probabilistic classifier. And the idea here is that the output of our function is not just the classification is class C or class 2 or class 3, but it says we have a probability for class A, we have a probability for class B, and we have a probability for class C, something like that, okay? And actually, the neural network, well, technically not a probabilistic, well, okay, well, all right. So the probabilistic classifiers, the output is a probability that the data has a particular class. Okay, so we write something such as the probability that the the random variable for our of our new classification. So this is the random variable t for our basically new observation is equal to class C given our, so this will be given the values of the new observation and the existing training data. Okay, so this is our training data, right? We have our x inputs, all of our x inputs, and all of our t observations. This is our existing training data, and we want to know, what's the probability that the next one is going to do this, right? And basically, when you have a probabilistic classifier such as this, if it follows kind of the rules of a categorical distribution. You guys know the categorical distribution, right? Or maybe? Okay. Maybe not. I don't know how much I can say. All right. So we have the categorical distribution, which basically you just kind of have a vector of the, what do you say? Basically, you have a vector of probabilities, and you might call that pi. And the rule is that the pi's have to add up to 1, and each pi is between 0 and 1. Right? Okay. And so basically this follows the rules, so that basically the probability of t equal to c given x, 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 and t, the sum of these have to add up to 1, and it also has to be between 0 and 1. Okay, and so the Bayes classifier is, we're going to use Bayes' rule to define what this is going to be. Okay, so for the Bayes classifier, we're going to say that this thing okay, so the way we, oops. The way we classify this is based on Bayes' rule. Right? So basically A given B is going to be, all right, so if we remember Bayes' rule, we have probability of A given B is equal to the probability of right? So we're basically going to apply this type of thing here, and it's going to be the probability of getting x new. This is the probability. I'll annotate this so it makes sense when you go through it. This is the probability of our our new observations x, okay, given, and we're going to put everything else on this side, which is going to be given that t is in class C and the training data. So given our observation is from class C, okay, and we're going to multiply this by the probability that t comes from class C, our prior probabilities that t comes from class C based on the training data only. This is the prior probability that T comes from class C given our training data. Okay, and all of this, this looks ridiculous now. This is divided by basically the probability of B, okay? And so the probability of B is the probability of X nu given our training data. Probability of our observations, X nu, given our training data, okay? So let me just kind of write this in a slightly neater form. It's exactly the same thing, but without the blueprint here, okay? Okay, so this is, all we're doing is we're using Bayes' rule to figure out, what's the probability that, based on this data, X nu, that our classification is class C, okay? And we just, and it's going to be, okay, it's the probability that if we have class C, what kind of observations X will we get? So what kind of observations does class C produce, okay? And then we multiply that by the prior probabilities of that we even get class C to begin with, okay? And then we divide that by the probability of all possible X nus that we could get based on our training data. I don't know if that makes sense. Okay, this part here, okay, this is basically, we're going to sum across all of the different classes that we have, okay? So this part here is going to be, this is going to become the probability of X nu given some the book uses this C prime, okay? But yeah, and so I'll use the same notation, but I fear that it's just confusing. But just so that, because I know if the teacher uses different notation from the book, it's a nightmare, right? Okay. So basically, this is like the probabilities of all possible x's, right? But the x's themselves can either come from, class A or class B or class D or whatever it is, right? And so we just have this generic letter C to say, maybe it came from class 1 or maybe it came from class 2, okay? So let's just say there's only, for this simplicity of this thing, let's say there's only 2 possible classes, and under class 1 you might get these kinds of x's, and under class 2 you might get these other x's. So to get the total probability of all the x's, we have to sum across what x's we might see under class 1 and what x's we might see under class 2, okay? And so this part, this x nu, we will expand into kind of a summation here. So this is the probability of all, what our x's are across the different things, okay? Because this is something we probably can't compute directly, okay? Or not probably, we can't, okay? So we cannot compute probability x nu directly given x and t. So we compute each, the probability of x nu across in each class to compute. Okay, so we will. So this is the idea here. Okay. So let me let me talk about this part. Where did this part go? This part is the prior, right? The prior probability that T comes from class C given our training data. Okay. So let's talk about the prior term. This is probability that T comes from class C given our training data. Okay, this is that our next observation T new comes from class C given our training data. Okay, and so we have a few options, and really this could be anything. This could just represent what you believe is the distribution of class class C. Like if you believe the whole world is all one class of people, then if that's your prior belief, then that's going to affect what we have. Okay, now so based on the training data, we have a few options. Okay, so a few options for this. Okay, one is the uniform option. Okay, and this is however many classes we have, each of these probabilities are equally likely, right? In the deck of cards, there's four classes, 4 suits. Each suit is equally likely. So we could say the probability here is just going to be 1/4 for every single class. Okay, or if maybe there's 2 classes and you think they're equally likely, you can just say 1/2, 1/2. All right, that's fine. Okay, so this is each class's probability. Is that how you write? No. Just I'm like, this is not right. Okay, each class's probability is just equal to 1 over C. C being the number of classes. Okay, so that's one way. Okay, and then the other one is kind of like your weighted, or your what we call the class size prior. Okay, and this basically is you count how many are in that class, and that's divided by how many total you have. Okay, so we would write the probability that T new is equal to class C given our training data is going to equal the count in class C. Okay, how many observations in class C divided by total number of observations. Okay, so let me just do a little small example here. Okay. So let's say we're going to build a Bayes classifier, and we'll do it. We'll do okay. We'll just So we'll say Bayes classifier, and we're going to look at. We have x1, which will be someone's height, and we'll have x2, which is someone's weight. Okay, and then the classes T sum n will come from either will either be an adult or a child. Okay, so we're going to look at someone's height, someone's weight, and we're going to say, okay, is this person an adult or a child, right? So you see someone weighs 60 pounds and is 4 feet tall. I don't know how much is this 60-pound person supposed to be? You'd say, oh, okay, well, probably a child, right? Someone is 5'7", weighs 140 pounds, probably adult, okay? And we would come up with some kind of number for these things. Okay. So let's say our training data, okay? So our training data consists of, has 12 observations. And let's say in our data, we have 4 adults and 12 children. Okay? And so based on our training data, because we're assuming that our training data is being randomly taken from the population, so whatever population this is, I don't know, maybe we're getting values from I don't know, some place, okay? So this is, if we assume our training, yes?
Is that 16 observations then?
Oh, I'm sorry, yeah, 16 observations. I don't know what I'm talking about here. Okay, yeah. So our training data has 16 observations. So, if we're assuming our data, is a random sample from the population, it makes sense to say, well, then future observations, the probability that we're going to get an adult, T new, will be adult, it would be 4 out of 16 or 0.25, and the probability that the next observation will be child is going to be 12 out of 16 or 0.75. Okay, now obviously if you know that your training data is not representative of what your future observations are going to be, then you'll want to take that into account and modify these probabilities. Okay, but if we're assuming the observations that exist in our training data are representative of future values we might see, this makes sense. Okay, okay, so that's what we use for the prior term. Okay. Okay, and then so now we want to talk about the probability of of this thing, our next value given is in class C and our training data. Okay. Okay, so this is now our class conditional. Okay. And which is kind of our likelihood term. So here we're going to basically, this is saying if we know an observation comes from a certain class, okay, given our data, what kind of distribution do we have for the x values, right? So this is, what is the distribution of x for data that come from class C. Okay, so and a simple example would be, so in our case, okay, so let me just kind of distinguish between the regular Bayes classifier, which in practice is not used very often. Okay, regular Bayes classifier. This we would say, our x, it's x sub h for height and x sub w for weight, right? don't know if we want to make this a thing. So, and basically our x's will come from, now it's a multivariate normal, right? Well, maybe it's not normal, okay? I don't know. I guess not necessarily normal, but we might assume that the distribution of heights and weights come from a multivariate normal, and maybe that's a bad assumption, okay? But we like normal distributions because they're nice to work with, right? So we can say, you know, the distribution of heights and weights come from a multivariate normal, okay? And so we would say, okay, our mean, and we would need the average height for all, and this might be the for class adult, okay? So I don't know, mean height of all adults, I don't know, we'll say 67 inches, that's 5'7", and mean weight of all adults, I'm making numbers up, 150 pounds, okay? I have no idea. Okay? Huh? Is that no good? All right, and then the our standard deviation, our sigma matrix includes the what? It includes the variance of height, I don't know, 4.5 inches squared, okay? And then our variance for weight, I don't know, 30 pounds squared, making up. Okay, and then there's some kind of covariance term, right? Because in general, we would say as someone gets taller, their weight goes up, and as someone gets shorter, you know, their weight goes down. In general, that's what we would expect to see. And then so there's some kind of covariance term, right? And I have no idea what the covariance is between here, but we'll, you know, 0.8 times, or maybe 0.6 times something, something, something. Okay, so this is, I'm just going to write covariance term, okay? All right, because I'm making this up, right? And this is, it's normal given that our class is equal, I guess I have to write that T nu is equal to adult. Something like that. Is that okay? And then I would make a similar type of distribution for the class if the class is a child, okay? You know, the mean, I don't know, mean height of all children, whatever that is, okay, and the mean weight of all children and the covariance term there. We have a few ways to go about this, okay? So these, you know, I just kind of made these numbers up myself, right? When you're doing these numbers are supposed to be based off of your training data. Your, you know, when you actually do, you know, I made up these. So in this example, I made up the mu and sigma terms in our normal distribution. Okay, and in practice, we use our training data to come up with mu and sigma. Okay, and so we have a few options. Okay, probably the most straightforward option is you would use maximum likelihood estimates of the mean and the sigma, you know, covariance matrix, right? Variance covariance matrix, right? So one option is to use maximum likelihood estimates of mu and sigma, right? So when normal distribution, the maximum likelihood estimate for the mean is the mean of your data, okay? And then the maximum likelihood estimate for the variance covariance is your basically the variance covariance of your data where you treat it as a population. Yeah. So I think could be wrong there, so that's one option. Okay, and then the other option, which we kind of covered briefly, but we didn't get really in depth on it so far, and I'll have you guys try to take a look at it in your homework, is we could also take a Bayesian approach, or Bayesian approach to estimating mu and sigma. And in that case, rather than getting a point estimate for mu and sigma, we would actually have a distribution of possible values of mu, saying that these values of mu are more likely, and these values of sigma are more likely, and these other values of mu and sigma are less likely, right? So another approach is to use a Bayesian approach where we get distributions of mu and sigma. Okay, is that all right? So let's just, so this is the regular Bayes classifier. The naive Bayes classifier this one, I would say, is used more in practice, makes a bad assumption, makes a bad but useful assumption, okay? That x1 and x2, that the x variables are independent. We'll say the x variables are conditionally independent. Okay, so what that means is that, given class adult, x for height is independent of x for weight. Okay, or given class child, x height is independent of x weight. Now that's a bad assumption. That's a bad assumption, but it makes our work easier. Okay, so when you draw contour plots, right? So if x1 and x2 are not independent, are dependent, then you might get contour plots that go at angles. Okay, if x1 and x2 are independent, then you might get circles or you might get ellipses, but the axes of the ellipse are always going to be parallel to the axes of the of x1 and x2, right? So you might have something like this, okay? If they are dependent, or but over here in your variance covariance matrix, so sigma is going to have variance of x1 squared and variance of x2, or I'm sorry, variance of x1, variance of x2, and over here you have covariance x1, x2, and covariance down here. Over here, your sigma matrix is the variance of x1, the variance of x2, and what do you have in the corners? 0, right? Okay. So what does that mean for our thing? That means that the probability of of x given that t is from some class and our data, okay, this becomes, what it becomes is we get a product of normal distributions. So you get the normal distribution where, so let's say we're saying the height is, we're doing class adults. You would say, you know, x sub h has a mean of, how did I write this on the previous slide? You know, so it has a mean of 67 and standard deviation, what did I write? You know, 4.5 squared, okay? And you multiply that by, what's the PDF for this, right? Times that the mean for weight is whatever number I use, 150, and standard deviation 30 or something like that. Okay, so now you have the PDF for this times the PDF for this. Okay, and you have no covariance between the height and the weight. Okay, so you know, thinking about people, we know that this assumption is wrong. It's incorrect to assume that someone's height is completely independent of their weight. Okay, so why would we make this assumption? Okay, well, the thing is it makes our life easier, especially with the covariance matrix. So with two x1 and x2, there's only one covariance term. But let's say you had 10 x variables. Okay, then you would have a whole bunch of covariance terms, right? You've got covariance between x1 and x2, x1 and x3, x1 and x4. You've got a whole bunch of terms and a whole bunch of parameters to now estimate. And the more parameters you have, you need more and more and more data to try to get accurate estimates, right? And if you don't have that much data, your estimates are really going to be wonky. So by making this assumption, it reduces how many variables that parameters you need to estimate, and you can get fairly precise estimates of what these variance things are. We know that the covariance terms are wrong, but the resulting model is more useful to us because we're getting better estimates of the mean and the variance terms, even if we know our covariance terms are completely off. Okay. All right, so this is kind of the naive Bayes classifier overview here, and then on Friday we'll take a look at it in practice and stuff.